Okay, the last video for this unit is on work and power. We talked about work before in first semester. Work is the movement of energy. We're going to go into a little bit more of that, looking at how you calculate work here. Okay, so if a force is exerted on this backpack and cause it to move a distance, it does work. Okay, if you apply a force and make it move a distance, you do work on an object. So if you hold something still and it doesn't move, you don't do any work on it. And you can think of it in terms of that energy piece as well, where there's no energy is transferred. But so if it doesn't move, there's no energy being transferred. So there's no work done on the object. So work is equal to a constant force exerted on an object in the direction of motion. So that force times the displacement that it moves. And thus the equation work is equal to force times distance. Okay, so work is the change in energy in a system. It can be positive or negative. If energy is done by the system, okay, if energy is gained by the system, so something is being done on it, the work done on the system is positive. So if it gets squished, you push on something, the work done on the object is positive. Whereas if something expands and it exerts energy outward, the work done on the system is negative. This should ring a bell from you before because we talked about this in the first semester. All right, so then we look at this thing called the work kinetic energy theorem. The work kinetic energy theorem says that the work done is on an object that results in a change in kinetic energy. Okay, so really you're looking at it usually a change in velocity. So the work kinetic energy theorem can be described as the following, which is just the work is equal to your change in kinetic energy. Okay, that's what's called your work energy theorem. Work is equal to your change in energy. Okay. Throughout the process of doing work, energy can move between the external world and the system. Okay, again, if the world does the work on the system, the work is positive and the energy of the system increases. However, if the system does work on the external world, releases energy, W is negative and the energy of the system decreases. Okay, so the work is the transfer of energy by some kind of mechanical way. Right, calculating work. So this equation only holds true for the force that's exerted in the direction of motion. So it doesn't necessarily work with something that's in orbit because you do have a part of a force that's at an angle. Okay, we're not going to deal with this math, but just understand the force that applies the work is only in the direction of the motion. So perpendicular force doesn't change the speed of the object, it only changes the direction, so that the kinetic energy is constant. So using the equation work is equal to change in kinetic energy, if the force is acted at an angle and it doesn't change the velocity, it doesn't change your kinetic energy, so your work doesn't change. There is no work done. Okay, so like on the orbit. Okay, so the force and the direction of the motion are at right angles, so there is no work done actually on it. All right. So because the work done on an object equals the change in energy, work is also the same unit as energy, which is joules. And a joule of work is done when a force of 1 Newton acts on an object over a displacement of a meter. So an apple weighs about a Newton. So if you lift an apple a meter above the ground, so about a little over 3 feet, you do 1 joule of work on the apple. All right, so now we're going to do a sample problem here. Looking at a hockey puck, 105-gram hockey puck, so 0.15 kilogram hockey puck, is sliding across the ice. So a player exerts a constant force of 4.5 newtons over a distance of 0.15 meters. We're going to look at how much work does the player do on the puck, and then what is the change in the puck's energy. Okay. So we've got to look at the problem first. So we're going to kind of do a little picture. So you have your hockey puck. We have our x-axis. So we have, if we look at our vectors, we have a force being applied in the x direction, a distance that the object is moving in the x direction, when the contact is applied. Okay, so it's going to the right. So force and displacement are going in the same direction. You're going to have positive work done. All right. So we know that the mass is 105 grams. We know that the force applied is 4.5 newtons. We know the distance that the force is applied is 0.15 meters. What we don't know is the work done and the change in kinetic energy. So we know work is equal to force times distance. That's the first problem we're going to use. Okay. So we substitute from work equals force times distance, a force of 4.5 newtons times a distance of 0.15 meters. So work is 4.5 newtons times 0.15 meters. So the work done on the object is 0.675 newton meters, which is 0.675 joules of work. Okay, force times their displacement. Okay, so that's the first half of the question. Work is equal to force times displacement. Now we're going to look at what the change in kinetic energy of the hockey puck. So we're going to use that work energy theorem to determine the change in energy. So again, we're looking at work is equal to change in kinetic energy. We know the work, 0.65 joules, which is your change in kinetic energy, is 0.65 joules. Okay. So that it's the same answer. So if you know your velocity, you can actually figure out your initial velocity, you can figure out the final velocity. Okay, so we're going to find the final velocity of the puck. And since we know our kinetic energy final, we know our work done, which was the change in energy, and that was 0.675. And we know since it's starting from rest, the initial kinetic energy is 0. That means the kinetic energy final is 1/2 m final velocity squared. Our kinetic energy final is 0.675 joules times 1/2 times 0.105 kilograms. That's the mass of the puck, times v squared. We do 1/2 of 0.105 kilograms, we get 0.0525 kilograms. Now what we're going to do is we're going to take the square root, because we got to isolate v. We're going to take the square root of 0.675 divided by 0.0525. And what you end up with is a velocity of 3.6 meters per second. So that means when the force is no longer applied, the hockey puck is traveling 3.6 meters per second. Okay, so you can go back and kind of review this if you need to. Okay, all because our change in kinetic energy is 0.675 joules. All right, so looking at graphs for this. So a graph of a force versus displacement graph can help you get the work done by a force. Okay, and if you think back, work is force times distance. So force times displacement gets you the area under the curve. Okay, so the area under the curve of a force versus displacement graph will get you the work done. So in this case, the force applied is 20 newtons. The displacement is 1.5 meters. So 20 newtons times 1.5 meters is 30 joules of work done. Okay, now this one, we have a changing amount of force. So now we're looking for the area of the triangle. So this one is, instead of just base times height, needs to be base times height divided by 2, or 1/2 base times height. So our top force is 40. Displacement is 1.5. So 1/2 of 20 times 1.5 is 15 joules of work done over this 1.5 meters. Okay. So the work done is the area under the curve of a force versus displacement graph. All right. So Newton's second law of motion kind of relates to the net force. Newton's second law, F equals ma, force equals mass times acceleration. So the work kinetic energy theorem relates to the net work done on the system to its energy change. When you change energy, you do work on an object. Okay. All right. So now the last part is, how fast do you do work, otherwise known as power? So power is work done divided by time. How fast do you do work, or how fast energy is changing forms? So in other words, power is the work that you do divided by the time it takes you to do that work. Or it's also represented by how fast you do and you change energy. The unit for power is the watt, W-A-T-T. So in your light bulbs that have 30, 60, 90 watt ratings, that's how fast energy changes. So because power is how fast you do work, it's also looked at as the rate of change of energy. So if you're given a kinetic energy versus time graph like this one, okay, the power is the slope of the line. Change in energy over time. Power is change in energy over time because work is change in energy. So the power generated by this motion is the rise over the run. The rise is from 0 to 45.36 joules. The time is about 0.9 seconds. So power is 451.36 divided by 0.9, or about 501 watts of power. Okay, so if you have an energy versus time graph, power is your rate of energy change over time. Okay. So a power thing, you can climb stairs. Okay, so we have 3 students shown here. The girl who's hurrying up the stairs is more powerful than both the boy and the girl who are walking up the stairs. So even though the same work is accomplished by all 3, they get to the same height. The girl accomplishes in less time and thus develops more power because she has to go faster. Because really the work that they do is just the work to get them from the bottom to the top. That's all they're doing. And in the case of the 2 students walking up the stairs, both accomplish the same amount of work in the same amount of time. So again, the unit of power is the watt. A watt is a joule of energy transferred in a second. Okay, a watt is a really small unit of power. So a glass of water weighs about 2 newtons. So if you lift it half a meter to your mouth, you do a joule of work. Okay, because a watt is such a small unit, power is often measured in kilowatts. 1,000 watts is a kilowatt. Okay, so when force and displacement are in the same direction, power is also equal to force times distance over time. Distance divided by time is speed. So power is also force you apply times the speed it's traveling. Okay. So your muscles can't exert extreme large forces, nor can they move very fast. So you have to have a combination of moderate force and moderate speed will produce a large amount of power. And don't worry about that part. Okay, so the formulas that you need to look at here is power is force times distance. Okay, and power is change in energy over time. Oh, excuse me, this should not be power. This is work is equal to force times distance. A revision here. So power is work divided by time. Power work divided by time. Power is also equal to the change in energy over time. So your change in energy, typically you're changing kinetic energy over time. So those are your formulas. Those are your 3 videos for Unit 6. Make sure you answer the questions on the formative assessment, and we will talk to you in class.